Modern data science lets us build incredibly powerful mathematical engines. We construct high-speed machine learning models capable of processing terabytes of information in milliseconds. But inside an actual organization, many of these high-performance engines end up parked in a garage, completely ignored by the people who were supposed to use them. A mathematically perfect algorithm has zero value if the organization refuses to adopt it. This is why the first step in solving a data problem involves no code at all. You must design the solution, drafting a structural blueprint to determine the best way to solve the problem in a practical, real-world setting. That setting comes with strict boundaries. Every project operates under a finite budget and an unyielding deadline. But the most volatile constraint isn't financial or temporal, it's the end user. People carry behavioral friction, deeply ingrained habits and biases that dictate whether they will actually interact with a new tool. Junior engineers frequently overlook this human element. They build unnecessarily complex, black box models to solve straightforward issues, optimizing for mathematical elegance instead of daily usability. True engineering value comes from doing the exact opposite. The goal is to deploy simple, highly actionable solutions that untangle complex, real-world problems. When a business stakeholder approaches an engineering team, they usually present a very narrow request. They might say, "Our sales are dropping, build a new recommendation algorithm." Taking that request at face value is dangerous. It represents only a fraction of the actual situation. That initial demand for an algorithm is just the tip of the problem iceberg. It is simply the symptom the stakeholder can easily see. The bulk of the threat lies beneath the surface, hidden deep within the operational layers of the company. Dropping sales might actually stem from a flawed pricing strategy, poor customer segmentation, or severe issues with product quality. If you build a technically advanced recommendation engine for a company that is pricing its products out of the market, the project will fail. You have successfully solved the wrong issue. To prevent this, data scientists treat problem understanding as a rigorous discipline. It requires asking probing questions and mapping the full business context before committing to any architecture. Effective solution design forces engineers to prioritize human-centric problem framing. Without that operational clarity, even the most advanced code is a waste of resources. We can see how these human variables map directly onto standard technical pipelines, like the cross-industry standard process for data mining, or CRISP-DM. The cycle begins with business understanding. This is where vague corporate objectives must be clarified. This stage cannot be completed by passively taking orders. It requires critical questioning and active listening to translate loose business needs into a structured analytical problem. Next come data understanding and data preparation, traditionally the most time-consuming technical stages. Finding anomalies and handling missing values across millions of rows requires extreme diligence. You have to approach the raw data with genuine curiosity to uncover why specific trends or inconsistencies exist in the first place. That clean data feeds into the modeling phase, the central pivot of the entire pipeline. Selecting an algorithm is rarely a pure mathematical certainty. It is an exercise in human judgment, balancing computational cost against accuracy and interpretability. Finally, the pipeline concludes with evaluation and deployment. A model only generates value when people use it. Deploying it successfully means you have to influence stakeholders and manage the organization's inherent resistance to change. The CRISP-DM framework tells an engineering team exactly what needs to be done, but their communication and analytical judgment dictate how effectively that pipeline functions in reality. Managing those modeling trade-offs requires a structured approach. In data science, we can evaluate model viability using a standard strategic tool, the SWOT matrix. We begin by analyzing the internal factors of a specific model, its intrinsic strengths and weaknesses. A model might boast incredibly high predictive accuracy as a strength, paired with a severe lack of interpretability as a weakness. We then map the external factors, the opportunities and threats that will impact the model once it leaves the lab. Deploying this model might present an opportunity for widespread process automation. Conversely, it could face threats like strict data privacy regulations or intense stakeholder resistance. Let's compare a highly complex black box deep learning algorithm against a simpler logistic regression model. The deep learning model might offer superior theoretical accuracy on paper, yet during a SWOT analysis, it is often rejected because the massive computational cost or lack of transparent logic makes it too risky for business leaders to trust. The simpler logistic regression model frequently wins out. Its transparent logic makes it significantly easier to explain, maintain, and adopt in the real world. Highlighting a model's weaknesses and external threats is not an admission of failure. It is a mandatory requirement to ensure the final product is practical and sustainable. We can see this strategic alignment at work at Netflix. As their streaming platform grew, their massive content library created an unexpected data architecture challenge. Netflix discovered that severe user choice paralysis, rather than a shortage of content, was the actual driver of audience churn. Netflix recognized they needed a strategic pivot. Their engineering goal shifted from simply predicting viewing preferences to actively simplifying the user's decision-making process. This required a complete reorganization of how content was delivered to the screen. Utilizing a design thinking framework, Netflix prototyped this user interface integration simultaneously with their back-end algorithmic development. They focused heavily on actionability. The algorithm's output was translated into intuitive categories, like the because you watched row, replacing raw probabilistic scores. Post-launch, Netflix utilized extensive A/B testing across different user groups to measure actual behavioral responses to the recommendations. This continuous monitoring fed directly into an iterative implementation cycle, allowing engineers to constantly improve the system based on live user feedback. Today, a massive portion of Netflix's viewing is driven by these algorithms. Their success relies entirely on translating highly complex back-end models into simple, user-centric experiences. There's a sharp contrast between an isolated lab environment and enterprise deployment. Real-world data is chaotic, unstructured, and relentless. Implementation is the critical phase where theoretical models are finally subjected to these extraneous, real-world variables. For an implemented model to succeed, it must fulfill 3 core requirements. It has to be accessible, understandable, and usable. Achieving this at scale requires foresight. Scaling up a model introduces severe operational dangers if the system's capacity isn't planned for in advance. A model running perfectly on a small dataset frequently chokes when deployed against millions of records, causing catastrophic failures. Infrastructure and volume limits must be mapped as constraints during initial design, long before code is pushed live. The controlled safety of a local Jupyter notebook offers no protection against the harsh strain of full enterprise integration. An algorithm sitting quietly in a report has zero business value. Its true effectiveness is only proven when it survives the demands of actual, scaled conditions. To mitigate the risk of widespread failure upon deployment, organizations rely on pilot testing. By restricting the initial rollout to a single department or a specific user segment, teams can gather targeted behavioral feedback and identify system flaws before a company-wide launch. During these pilots, teams often encounter a massive roadblock: technical communication. Using complex jargon creates deep confusion and quickly erodes stakeholder trust. Data scientists must translate complex statistical outputs into straightforward terms. Grouping continuous probabilities into distinct, actionable categories empowers users to make rapid decisions. This leads directly to the core human variable in any data architecture: change management. End users naturally resist new technical systems because they fear uncertainty. Navigating this requires empathy and persuasion, making these soft skills hard requirements for data professionals. It also requires treating implementation as a continuous, iterative process, rather than a one-time launch event. By analyzing how users interact with the tool, teams create a continuous feedback loop, harvesting behavioral data to constantly update and refine the model. A data scientist's ultimate professional impact depends on their ability to navigate the human and organizational systems required to deploy an algorithm and extract tangible business value.